Division of complex numbers in Cartesian form employs the complex conjugate. Learn how it is solved here in Mathematics of Engineering. In division of complex numbers in Cartesian form, it is necessary to know how complex conjugate works. Complex conjugate is denoted with a bar, and it is basically the flip of sign of the imaginary part of the complex number. For example, if z is negative 25 plus 15i, its conjugate is negative 25 minus 15i. Negative 25, which is a real number, remains as negative 25, but positive 15i transforms into negative 15i. Another example is 30i. This is purely an imaginary number, and its conjugate is negative 30i. Next is if z is equal to negative 7. This is purely a real number, so its conjugate will still be negative 7. No change is done. Simplify the complex number I over 1 plus I. Since this requires division, we are to multiply the fraction by the conjugate of the denominator, that is 1 minus I. The numerator then becomes I times the quantity of 1 minus I. The denominator will have 1 plus I and 1 minus I. Note as well that the denominator becomes difference of two squares, which can be reduced into the square of the first term, 1, minus the square of the second term, I. Again, I squared is negative 1. Z then becomes 1 minus I squared over 1 plus 1. Simplify I squared to have I plus 1 over 2. In its standard form, we write z as 1 plus I over 2. The next example is 2 over the product of 1 plus I and 3 plus I. Before multiplying the conjugate, simplify the denominator first. Distribute the terms of the first complex number, and then multiply the exterior factors to have 3 plus I plus 3I plus I squared. Note that I squared is negative 1, so the denominator is simplified as 2 plus 4I. Now that z is simplified into 2 over 2 plus 4i, multiply the conjugate of the denominator, and have 2 times the quantity of 2 minus 4i over the product of 2 plus 4i and 2 minus 4i. Using the conjugate transforms the denominator into difference of two squares, which makes z as 4 minus 8i over 2 squared minus 4i squared. Simplify the denominator and get 4 minus 8i over 4 minus 16i squared. Again, I squared is negative 1. Factor out 4 from the numerator too, to have 4 times 1 minus 2i over 20. Reduce 4 and 20 to have z as 1 minus 2y over 5. Another example requires to simplify z of 1 over I raised to 2509. By the rule of exponents, distribute 2509 into both the numerator and denominator, where z would have 1 raised to 2509 over I raised to 2509. The numerator will be simplified as 1, giving z as 1 over I raised to 2509. Next is to convert the exponent of I into an even number. Thus, we factor out 1i, giving z as 1 over I times I raised to 2,508. You already know that I squared is negative 1. So I raised to 4 is just like I squared times another I squared, which is then negative 1 times negative 1, which is eventually positive 1. So what we can do with the large exponent is to have to be factored into 4 times 627 and simplify I raised to 4 as positive 1. So z is then 1 over I times 1 raised to 627, which is basically 1. Therefore, z is simplified as 1 over I. The next problem contains a combination of operations. With the other terms having denominators, we start the solution by simplifying the second term. Distribute the terms of 1 plus 2y and multiply them into the quantity, becoming 2 plus 2y plus 4i plus 4i squared. I squared is negative 1, so the second term becomes 2 plus 6i minus 4. Simplify the constants and get negative 2 plus 6i. With the second term already simplified, z then becomes 1 plus I over 1 minus I minus the quantity of negative 2 plus 6i plus 3 minus I over 1 plus I. Now take the LCD to have a unified denominator. The denominator is the product of 1 minus I and 1 plus I. Then take the equivalence in the numerator, which has 3 terms. We simplify each of the terms separately. The first term is 1 plus I times 1 plus I. By taking the FOIL method, we get 1 times 1 plus 1 times I plus I times 1 plus I times I. Simplify each and get 1 plus 2y plus I squared, where I squared is negative 1, and this cancels out with the constant. Thus, we get only 2i. The second term in the numerator has 3 quantities. Simplify 1 minus I times 1 plus I into 1 minus I squared using the concept of difference of two squares. The result is 1 minus negative 1, which is 2. This is multiplied to the first quantity, giving negative 4 plus 12i. The third term is then solved through FOIL method and get 3 times 1 plus 3 times negative I minus I times 1 minus I times negative I. This is simplified as 3 minus 3i minus I plus I squared, which is taken as negative 1 again, making the expression 3 minus 4i minus 1, reduced to 2 minus 4i. The denominator can also be simplified into 2 from difference of two squares, where the second term turns into negative 1. Z is then transformed into 2y minus negative 4 plus 12i plus 2 minus 4i all over 2. Distribute signs and get 2y plus 4 minus 12i plus 2 minus 4i all upon 2, and get 6 minus 14i over 2. Factor out 2 and get the final answer for z as 3 minus 7i. The next example has z equal to 2y times the quantity of I minus 1 plus the cube of the quantity root of 3 plus I plus another quantity of 1 plus I multiplied by 1 plus I. Take note that the second term and part of the third term have bars on top of the quantity. The bar means complex conjugate. So the second term becomes root of 3 minus I, and the part of the third term with bar becomes 1 minus I. Simplify each term starting with 2y times I minus 1, which gives 2I squared minus 2y. I squared is taken as negative 1, resulting to negative 2 minus 2y. The second term is the cube of the root of 3 minus I. Solve this by separating the quantities into lower degrees to easily simplify them. With the square root of 3 minus I, we take the square of the first term, root of 3, then double the first term with the second term, negative I, plus the square of negative I. The terms then are reduced into 3 minus 2y times the root of 3 plus I squared, which is taken as negative 1. So the square is 2 minus 2y root of 3. Now solve the second term by multiplying the first complex number and get root of 3 times 2 minus 2y root of 3 minus I times the same quantity. Distribute the exterior factors and get 2 root of 3 minus 2y times root of 3 times root of 3 minus 2y plus 2I squared root of 3. Root of 3 times root of 3 is 3, and I squared is negative 1. Thus, the second term becomes 2 root of 3 minus 6I minus 2y minus 2 root of 3, which is then reduced to negative 8I. The last term of z is again the difference of two squares, which gives 1 squared minus I squared, which is also reduced as 2. Finally, z is negative 2 minus 2y minus 8I plus 2, which is reduced to negative 10I.